All right, we're 406, so I'll answer, I think it was Isaac's question about the quiz. So if you want to scroll up in the chat, you can see that there. So the question is, regarding the quiz, is it going to be based on this week's learning materials, or is it going to be based on the 3 weeks of learning? The short answer is this week's learning. However, to be able to understand this week's learning and to be able to apply this week's learning properly, you need last week's learning. So being able to draw good free body diagrams, understanding 2 force members particularly. 3 force members would be good, but you can do the problems without knowing about 3 force members. And of course, the stuff that we did on equilibrium back in Introduction to Mechanical Engineering. So yeah, short answer is just this week's material, but the long answer is this week requires last week and stuff you did in Intro to Mech. So it'll look very similar to the one that I've already given you. So it's just the one question. So it'll be some kind of frame or machine, and you'll be asked to calculate the reaction forces at various locations within that frame or machine. Okay, so no, there shouldn't be any surprises. That's not the way I operate. One question, but multiple. Well, let's go and have a look at the question that's there as an example. Okay, so it's just the one question, and you're asked to basically analyze that machine or frame. Okay, so might be find the reaction forces at all pins, or 1 or 2 or whatever. Okay, and it will be some kind of frame or machine that has multiple parts that interact with each other. So you'll have to draw multiple free body diagrams in order to do the problem correctly.
Hi, Derek.
Yeah.
Will you provide the answer for the example?
So will I provide the answers? Yeah, we're going to work through that tonight. And then after that, I'll upload my full solution. Because as I was running a bit, as you see, some of the things I uploaded, I'm a bit behind where I wanted to be. And actually, when I was doing the solution for this problem, as I got to the end and did the think about and check the solution part, I thought, hang on a second, those numbers don't seem right. So I thought, oh, well, I'll just leave it as it is, and we can go through my incorrect solution and we can see if we can find out where the problem is. It was just a simple rushing error where I'll let you find it when we get to it. And also I've got a couple of solutions that a student sent to me earlier on a week or so ago. And I said, oh, I won't answer those now because we haven't really got to that material yet in the modules. But if it's okay, I'd like to use it in the class. And he said, sure, that's fine. So thank you to that student who's allowed us to use his incorrect solution to have a look at. But yes, I will post up the proper fixed solution when I get it done. Okay, so how did you guys go with the tutorials and the example problems last week with 2 and 3 force members, particularly 2 force members? That's the most important thing to get right. Can anyone recognise which is the 2 force member in the quiz example problem here?
A and B.
AB. Okay, yep, so this member here, AB, all right. Let's have a quick look at 2 and 3 force members. Okay, so thanks, Nora. So they weren't too hard to understand or solve, just took a while to get through them all, yeah. Especially if you take the time to do good, neat, clear free body diagrams like I do and like I would like you to do. Sorry, I keep looking over there because that's where I can see all the names. I should be looking at the camera. Yeah, so that's why I've given you longer to do the problems this semester. So last year they had like half an hour plus 15. In this session, I've given you 45 minutes plus 15, but the problems are much the same. But I expect you to do good free body diagrams, and we'll award marks for that. So that's why you get a little bit longer. So what I propose to do by way of a review of last week was just to go through this this problem 3 and talk about 2 3/4 members again, okay, and talk about the interaction between different components in a frame. So if you would like me to do that, can you please type yes, or if you don't want me to do that, type no in the chat, just so I get a feel for whether this is the right thing to be doing or not. All right, so we've got 3 yeses already. So note that there is the video solution here that you can go back to, but we will have a look at it now. All right, awesome. So please explain what happens at A. Okay, yep, I can do that. Okay, we did in class, but don't get it. Awesome, thank you for letting me know that. That's important that I understand where everyone's at and can respond to that. What I did in my tutorial was to get students to draw free body diagrams and to upload them to the team site. So they're not going to have a look at what you've done and respond to that. So there was probably only about 10 or 12 students in my tutorials. And I know some of those students are here tonight. So if those students feel like, oh, I've done this, I don't need to listen, then by all means go and do something else. But for those who were in different tutorials and didn't quite get it, we might do that again now. All right, so what I'd like you to do is to have a go. Don't look at any of the solutions that you may have seen before, but just from your memory of what you learned last week, now have a go at drawing your free body diagram of just the beam. Okay, so don't do any calculations, just draw a free body diagram of the beam. And then I'll get you to upload them into the folder on Teams. I'll just go and check that. All right. Okay, so I've posted that link to this folder, Lec1 week 3. So when you've had a go at drawing the free body diagram, we can have a look at what you've got. Okay, so when we talk about a free body diagram, right, that first word, free, right, means that it's free of its connections to other things. Okay, so if I say draw a free body diagram of the beam, then I mean just the beam alone. Okay, and then we replace the interactions with other components with the forces and or moments of interaction that are generated by the connections to those other components. Okay, don't forget to upload your solution when you're done. Okay, we've got a couple there. Thank you. So I can look at what people have done, and usually what I find is that the errors that people make, I've seen them dozens of times before. Okay, so it's very rare that I've come across a mistake that I haven't seen before. So don't worry about getting things incorrect. It helps me to help you if I can see where you're at. Otherwise, I'm just guessing where you're at. All right, it's 4:30, so let's start having a look at some of these things. So let's. So I know these two were in my tutorial, so I might not look at theirs yet. So I'll grab this one. Okay, so a couple of things here. So this is good. So we've got a pin connection here at Yeah, so I've got a pin connection at C, so that's good. So only horizontal and vertical reactions. Okay, yeah, angle in radians. Yes, no problem. You can fix that up later. Be careful of this angle here. Okay, so we had this small error in the in one of the tutorials as well. So the angle that you've actually calculated here is the angle from A down to this point here. I'm not sure if you can see that where I'm pointing. Right, so your angle is not quite correct. Yeah. Right, so the angle between AB and the top of the beam, or the center line of the beam, will actually be here. We should have 3.2 minus 0.2 over 4 to get this angle here. Right, so what you've actually calculated is that angle here, that angle. Now, the reason that I was able to pick that up, partly because I know what the solution is, but also because your free body diagram is pretty good. Right? It's a fairly neat, clear free body diagram. Now, as I've said, I think last week in the lectures and probably in the tutorial as well, is that a problem with having questions like this is that when you guys, students, draw your free body diagrams, right, you can get away with being not so careful and neat with your free body diagrams because all the information is given on the question. Okay? But if you were doing this as a design task, right, if you're actually designing this, then you've got to put on all these dimensions yourself. Right? So you have to be clear about where things are. Okay? So we saw a few examples in the tutorial where, because the student hadn't drawn a nice, neat, clear free body diagram, we couldn't see this detail properly. Yep. All right, so the other thing that you've done here is to include the cable in the free body diagram. So that's in general not necessarily incorrect, but you know, I did ask for just a free body diagram of just the beam because that's what we're analysing. Okay, so what you should be doing is thinking about, well, if I'm going to draw a free body diagram of the beam, what force and or moment, if there is one, is going to be generated at the connection point here. All right, so other than that, that's good. Okay, so we've got good here. So the reactions at C, correct, because we've got a pin connection. As I was just saying in the previous, when looking at the previous solution, take your time to draw your free body diagrams neat and clearly. Right? So here it's not so obvious what's happening, you know, with your dimensions. So you've got 0.2 down here, but point C is actually being shown above this 0.2. You know, and you've got the dimension here. I'm not sure where this 3.2 is going to. So just take that little bit of time, right, to make it neat and to make it useful. Right? And I'm not telling you this for my benefit, although it does help me to be able to mark your work. Right? If I can see it clearly and I go, oh, that looks really good, I can see everything you've done and I can easily give you marks. But it's for your own benefit as well. So when you're trying to solve these things, if you can clearly see on your diagram where things are, it makes your solution much easier, okay, and much more likely to be correct and less liable to error. So you can also see here, you've got 4 meters showing, but BY is some distance away from that. All right, and again, I think most people seem to be on the right track with regards to the force RB here that's generated in the cable. We're recognizing that this is a 2-force member in equilibrium. So therefore, the force will be along the line of action of AB. Not keep saying line of action. So the line of action of the force will be along the line joining A and B. But when we draw the free body diagram, we really should just draw the beam only. Okay. So we don't need to have all this other stuff confusing things. Right. So we've got an unknown here called RB, we've got an unknown here BX, we've got an unknown here BY, we've got an unknown here AY, we've got an unknown here AX. So all of a sudden, if we look at our free body diagram, we've got 1, 2, 3, 4, 5, 6, 7 unknowns. Admittedly, you might know in your head what's going on, but it becomes a bit of a confusing solution. Okay. All right, so that's good that you're kind of recognizing this RB as a two-force member, and everything else is looking okay. Just another point that I think I made in the tutorials is, so we've replaced this load component here with just a single force. Okay, so we've recognized that there's going to be a single force at the center of mass of this weight hanging down here. Okay, and probably most of you have just gone, okay, I'm only given a distance here, 4.4, so I'm going to put a single force here on the beam. Okay, and that's okay. And it's in this case what we need to do, but try and get into the habit, not so much in a quiz, although we should be asking quizzes like this, but during tutorials and when you're practicing, just stop and think, hang on a second, I've got a force here. If I actually represented this properly, what's more properly, what's it going to look like here? Is it going to be just a single point force here? What do you reckon this looks like it might be? What do you think's hidden behind this little green triangle? Any idea? Rollers and pins? Yeah. All right, so by the looks of things, it looks like there's two rollers on this gantry crane here. Okay, so, and in fact, there's probably another two on the other side. So this is an I-beam, okay? Not sure whether you recognize that or whether it's said in there, but because I see these double lines top and bottom here, and this has got to sit on something, then I'm looking at this and thinking, that's an I-beam, okay? So if this gantry is sitting on here, it's probably sitting on both sides. So there's two rollers on this side, two rollers on the other side. So in effect, this force that we've got here will be divided up between four rollers. So we'll have actually 4 point loads acting here. But in this case, we're just going to simplify it to one because that's all you can do. Yep. Okay. That's good. Nice and neat and clear. Just be take a little bit more time and just put a witness line here, right, so we know where this arrow goes. And yeah, that's good. Angle theta. All right, that's okay. I don't think I need to say much more about that one. So indicated here that RB is acting along the line AB. Good. Yep. Yep, so that's fine. That's a good one as well. Yep. Note here that we don't actually have to calculate the angle here. If you remember your 3-4-5 ratio triangle. Okay, so that side there is 3, the side there is 4, okay, because we've got 3.2 minus 0.2, so that height there is 3, this distance here is 4, so right? That's going to be 5. So when we calculate our components here, we could do, for our horizontal component, we could do 4/5 FAB. Vertical component, we could do 3/5 FAB. All right, so that's good. So this is what we need to be seeing for your free body diagram for the beam. Now I want you to draw a free body diagram post. So draw a free body diagram of this orange post here, and draw it on your page near your free body diagram of your beam that you've drawn, so that we can look at both of them together when you upload it. Also draw cable. Okay, so just while you're doing that, there's my solution for the free body diagram. Separate free body diagrams. Okay, so when you draw your free body diagram of the post, just assume that it's built in down here. Okay, so Isaac, I think you just said you're not sure you're right. So it's pretty right. I guess you probably got that from the discussion. But yeah, the only thing I would say is just be careful with this detail that you've got here at point B. You need to be probably need to be a bit more careful with how you represent that, so you make sure that you get your horizontal and vertical components in the right locations. Yeah, and also, so you've got up here this dimension. So here, we're not sure whether it goes to this point or whether it goes to this point where the end of this force is. Other than that, it's good. So we've got one question. Wouldn't the cable be a 2-force member? Yes, absolutely. That's what we've been talking about. Yep. So the cable is connected only at 2 points, so therefore 2-force member. Okay, interesting question. I'll not sure exactly what you mean. We'll think about that in a second. Okay, just wait for a couple more. All right, let's start having a look at some, and we can go to others as they come up. All right, so zoom in on that. So the thing with our free body diagrams of each of the individual components is that where we had connections between one component and another, we should be showing equal and opposite. Okay, so here we've got the forces that the cable is exerting on the beam. Okay, so what we're trying to show on this free body diagram are the forces that the cable exerts on the beam, whereas down here we should be showing the forces that the beam exerts on the cable. Okay, so these 2 points are the same, so what we should be seeing from one to the other is equal and opposite forces. Okay, so nice, neat free body diagrams, nicely drawn. That's excellent. But here, right, we've got a point that exists, the same point exists on the 2 connecting components. Right? So, as I said, the way I like to think about it is when we draw the free body diagram of the beam, we show what the cable is exerting on the beam. When we draw the cable, we show what the beam is exerting on the cable. Okay, so these 2 things, well, the forces here and here must be equal and opposite. Okay, because they're an action-reaction pair. Right, so Newton's 3rd law, I think. If you have an action, you've got an equal and opposite reaction. Right, so these points here are what we call action-reaction pairs. Same up here at point A. Okay, so where we've shown the forces here on point A on the cable, over here we should be seeing equal and opposite. So I think if you look at the problem and think, okay, this weight is pulling down here, this beam is going to tend to want to rotate downwards clockwise, so this cable is holding it up. Okay, So we've got this bit right. And then over here at the post, you can imagine, okay, this cable is being pulled down by the beam because of the weight. This cable is pulling down on the post. Yep. So over here, that's correct. Right? The cable is pulling down on the post. But on our cable, we should be seeing equal and opposite, because you can imagine that this cable is in tension, yeah? All right, and same down here. Right? So here we're showing the forces that the post exerts on the beam, whereas when we draw the free body diagram of the post, we should be showing the forces that the beam exerts on the post. Okay, so that's our original one. We haven't got the, so this is good. This is what we were looking at before, but we're now looking at the free body diagrams of the cable and the post. The only other thing is, this is a minor thing. Now, you've taken the time, you know, to draw things nicely. Right? Just have this line going through this point here at B. Right? You know, don't take that as too much of a criticism. It's just a little point that, oh, if I wanted to help you improve at anything, that's what I'd say. Other than that, excellent. Okay, so a couple of things. Good attempt. So you've got the pin connections here at RC, X and LCW, but just as I was saying to that previous one, you've got RCRX opposite, but RCY is the same on both. So you need to be very careful with these details when you're doing these problems, especially when you go and look at the example and the tutorial problems for this week. These details are really important, otherwise you'll get things wrong. Also up here at A, you've got this as a horizontal force, okay? Because this cable is a two-force member in equilibrium, the line of action of that force is along the line A to B, okay? So this force RA here will be along that line. So same as you've got drawn here. So here's, I assume this is your free body diagram for your cable, although you got RA and RB swapped around. But up here where we draw A at the top of the post, right, what we should see there is what the cable is exerting on the post. So it's not all of a sudden going to apply this horizontal force here. Yep. It's going to apply a force along this line of action, pulling down at A. So if I just go through my process now. So here, looking at my the free body diagram of the cable, two-force member in equilibrium. So therefore, the line of action of the force must be along that line A to B. And it's at B here. Force on the cable will be equal and opposite to the force on the beam here at B. So, okay. So the beam is now pulling down on the end of the cable B. So that will be like that. Okay. So that will be RB. Then at the other end, right, for this thing to be in equilibrium, force up here must be equal and opposite and collinear. So that force up here, RA, and RA will be equal to RB. Okay. And then if we now go to our free body diagram of point A, I can put that in there. Okay, and then at C, we'll just have the equal and opposite forces here. So we'll just have, so we need equal and opposite to RCX. That's on the beam free body diagram. And then RCY like that, and then our free body, our reactions down here. Okay, so that would be the free body diagram of the post. Okay, so if you know, to make this an even more practical problem than it is, right? In these problems, they never tell you why you're calculating these forces. But if this was, you know, if you were designing this gantry crane, then you need to size this cable or choose the material. You need to size these pins. You need to size this beam. You need to size the post. In order to do that, you need to know all of these forces that are acting. And ending up with something like this for the post, something like this for the beam, enables you to draw your shear and bending moment diagrams that we'll do in a few weeks' time. Is it safe to put the arrow representing RCY in the post free point C pointing at point C? Yeah. So I think you mean like this. Let me just quickly change that. You mean like that? Yeah. Yeah, so that's fine. Still the same line of action. Just looking at the problem, do you reckon we got the sense of RCY correct? Yes or no? Do you reckon we got the sense of RCY in our free body diagrams? So probably easiest if you look at the beam free body diagram. Do we reckon we got RCY in the correct sense? No, not. So I'm not meaning with respect to a coordinate system. I mean, is this force going to be acting up or is it going to be acting downwards? So we've got it shown as acting up. Can we just look at our free body diagram and work out whether that should be acting up or whether it should be acting down? Okay. Or another way to put the question, are we going to get a positive answer when we do the calculations or a negative answer? Okay, so one person thinks we've got it correct. So you think that what I've drawn here is correct. So somebody else thinks up is correct. Why do you think it should be acting upwards? Why do you think what I've got here is correct? Can you justify that thinking? Okay, thank you. Right. Yes, you need to think about what you're indicating in the chat, but that's not enough information to be able to determine this. Okay, so let me stop sharing for a second so you can see me. Right, so this is our beam here, okay? And let's imagine I don't have a string, but if I've got a cable coming up here holding this up, right? So it's essentially being held here. So if I go like this, pull down on the weight, where the weight is, what's happening? It's rotating about point B, yeah? So this, where I'm holding it here, this is point B. And this is the weight. What's happening at C? Moving up, right? So if this is going to be in equilibrium, what do I need to apply at C to stop that rotation? So I need to push down, yeah? So RCY actually acts downwards. Okay, so you need to look at the moment. So usually it's the moments that will tell you, right? Taking moments about somewhere. And that will tell you whether the sense of the force is correct or not. in most cases. Sometimes you can work it out just by looking at there's a weight acting down, and so therefore we've got to have a support somewhere. But in most problems like this, the information or the equation that will tell you, or the thinking that will tell you, will be looking at the moments. Yeah? So cable's up here, weight's down here, right? I've got to have a force out here. Force has got to be going down. Right? So if you go through to my solution, where are we? So you can see RCY comes out negative. Yeah, so here we can see RCY has come out negative. All right, one more question before we go and have a look at the quiz. Unless there's some questions from you guys. Right. What if I replace that cable and instead I put a member that looks like this? Okay, so that's my structural component joining A to B now. If I have that as my connection, does that change my free body diagram? Yes or no? Right, if I redraw my free body diagrams, so if I now copy and paste this over here, right, so that's now my component AB. Right, so it's not straight anymore. Do any of my free body diagrams change? Okay, so we're getting it. Awesome. So someone said no. Wouldn't the forces still act in the same way? Yes, they would. It shouldn't change the free body diagram greatly. Doesn't change the free body diagram at all. Okay, not greatly, doesn't change it at all. Okay. Yep. Any moments would all be the same as before. Yep. So because the key is, it's not the shape of the component that's important for a two-force member. So mostly we make them straight because that's the most efficient shape to make a two-force member. But sometimes, because we've got things in the way, we have to make them a different shape. Okay? So if we do a free body diagram of AB and it looked like this, then our line joining A to B is still this. Right? And we still have our RB in that direction along the line joining A and B, and we still have that. If you have any problem with any of what we've done now, ask a question, because having a good understanding of this relatively simple problem and just applying this methodically through the problems that are in the example problems and the tutorial problems and the quiz problem, it's just a matter of applying what we've looked at now tonight to those problems. Okay, so here's our quiz problem. And as we talked about at the start, I asked if you could recognize the two-force member in equilibrium in this problem. So the key thing to look for is a component that's connected at 2 points only, and there's generally no forces acting on it. Okay, so in this problem, the two-force member is member AB. So here, we're asked to determine the components of force at pins B and C. Right. How are we going to do that? What are we going to draw a free body diagram of? We've got lots of choices here. We've got this pulley, we've got the whole frame. We've got the 2-force member AB. Where do you think we might start with drawing a free body diagram? Okay, so our solution plan is the same as always, right? It's always nearly always a 4-stage solution plan. Draw free body diagram or diagrams. So up until the end of last week and today, usually you just drew one free body diagram and that was it. Now that we're starting to look at frames and machines where we've got components connected to each other, we need to draw free body diagrams. So like we did in the previous problem over here, where I did a free body diagram of the beam, free body diagram of the cable, and a free body diagram of the post, that's the kind of thing that we need to do here. For the problem that we did before, we were only asked to calculate reactions at B and C, so we didn't really need to draw any other free body diagrams. But we did just to illustrate how you do that. All right, so where would we start? What would we draw a free body diagram of here? Anyone want to type something in the chat? C and B, yep. Any other options? I actually didn't, but that's because I kind of knew what I was going to need before I got there. AB, yeah, okay. Any other options?
CA.
CA, okay, so okay, I'm not sure exactly what you mean by that. You mean just draw this whole thing as a free body? Should the pulley be on its own in a free body diagram? It can be, and in fact, that's what I did, and that's what I did first because I was thinking about teaching as well as just solving the problem. Yeah, you can kind of do the problem without drawing the free body diagram of the pulley on its own if you know how to deal with pulleys. But yeah, okay. So when it comes to looking at a problem like this, it can be a little bit difficult to know where to start. Right? So generally, what I would do is say, okay, what do I need to find out? Okay. You know, if this was a design problem, I need to know everything. Right? So you've got to solve everything at some stage anyway. But for a quiz or assignment problem or a textbook problem, and it asks you to solve for forces at particular places, then typically you would start with a free body diagram that includes those things. So a free body diagram of this beam or this component here, BC, is probably where I would start. Okay, but then you soon realize drawing that free body diagram that you can put in some reactions here at B and C, but you need to know about something, you know, what's going on with getting the load from here into that beam. Okay, I wouldn't necessarily start with member AB. I need to include the effect of AB in here, right? Because this is our 2-force member, okay? Well, too many places ahead. So if I start drawing some free body diagrams, would the pulley be, so that's it could be depending on what's happening, okay? So if there was no rope at the top here, right, and there was just rope wrapped around the drum, then I would say, yes, you could consider this to be a weight and a moment at this point here, okay? But what I've done is because there's a rope here, that goes over the pulley and then is attached to the wall. What we need to do is, so I'm kind of thinking ahead to having to solve for the unknowns on this component BC. So here's my load, and I want to know what the load of this rope is doing at this connection here, C, not C, I think I called it D. Yeah, right, so I've called this point here D. All right, so we're given the weight of the, or the mass of this weight. I can't remember what it was, 490.5, I think, from memory. Doesn't matter, just put in W. Okay, and that is pulling down on this rope. If this is a pulley, then we can consider this the friction in here to be negligible. Okay, so therefore that's free to rotate. Therefore, for some of the moments about D to be 0, this force up here must also be equal to W.
Minus W.
Sorry?
Minus W.
Not necessarily. Right? So minus W with respect to what? I haven't put any coordinate systems in yet. So I haven't said whether positive to the I haven't said whether to right is positive or to the left is positive. All I've done is indicate the sense of the force on the rope. Okay, so we know that if we're pulling, okay, so there's my pulley. If I pull down on this side, I need to be resisting pulling this way at the top here, yeah? And if it's going to be an equilibrium and there's no resistance from friction inside this pulley, let's get rid of that stick. So I'm pulling down on the right, so it might be on the left for you. So I've got to be pulling at the top here. So that rope's in tension, yeah? And so this one is W. So then we can look at, oh, I haven't put enough stops in, jumped ahead too far. So once we've got that equal to W, then we know that here's a pin connection. So we're going to have reaction components, right? No moment reaction because it's free to rotate, it's a pulley. So we've got a vertical component reaction and a horizontal component. Some of the forces in the vertical direction equal 0. So Rdy is W. And some of the forces in the horizontal direction equal 0. So Rdx is also equal to W. Yeah. All right, so now we can draw our free body diagram of BC. So I want you to have a quick go at that. I won't get you to post it up because we're running out of time. But just have a quickly draw what you think the free body diagram of BC will now look like. Okay. Oh, sorry. Just yell out. Don't put it in chat. Just yell out that I haven't shared my screen. Okay, so there's my free body diagram of the pulley. Now I can draw a free body diagram of the beam. So have a quick go at that. I'll give you until 5:40. Please have a go at it. Don't just sit there and wait. I won't post, I'll get you to post them up, but please just draw your free body diagram so you can compare what you do with mine. You don't, if you've got it, post it and we'll have a quick look at it. I wasn't going to do that because we're running short of time, but if there's someone got one there already, I'll have a look at it. Okay. All right, so Hee-chan, there's some problems here that need to be addressed. Thanks for sharing, by the way. So the end here, what's happened to the part that extends beyond beyond B? So if we look over here, we've got this whole member here is what we're analysing. Okay, so maybe you didn't quite understand the way the frame was drawn. So all from C to B to what I've called D on my pulley here, that's all one complete member. So you need to have that as well. The other thing is that we've recognised that RAB is a two-force member. So our force at B must be along the line joining A and B. Okay, so again, this is so good. We've got RCY and RCX here at the pin connection. That's correct. But you're just missing these forces that we've just calculated here. Okay. Without forces here, we've got nothing to be able to determine these unknowns. So this is good. I assume that the direction of this force here is along this line AB. Right, so if we start to have a look at what I've got now, so just the beam or this component, we just draw a simple outline of the shape, put on some dimensions. Right, start with our load. So we've got here RDY. So going from the pulley to the beam, we have these equal and opposite reaction pairs. Okay, so this RDY is the force that the beam, right, or this horizontal component here, is exerting on the pulley. Okay, so the pulley needs to be held up. Okay, so here's our pulley. We've got a rope pulling down on one side here, and this is our beam holding it up. Okay, and then if we draw our beam, take the pulley here, it's pushing down on the beam. So we have the equal and opposite down here. Right, and the same with the horizontal force. Force that we draw on the beam down here must be equal and opposite to this one. Right, and from what we've done here, RDY and RDX equal to W, so we can just replace just put the W at point D here. Yep. So yeah, so I think earlier on someone said, do we start with a free body diagram of the pulley? Yes, we can, and that's what, as you can see, what I did, just to illustrate this equal and opposite action reaction thing, and also that these forces here, we can just put them straight onto our free body diagram here. So, if I was doing this without teaching and using that as a solution to teach, I probably wouldn't have this separate free body diagram up here. I'd just have this as my free body diagram because I understand where they come from. Right? But anyway, so then over at C, we've got our reaction forces or reaction components. Give them some labels. And then at B, we need to put on the force here. So here, right, now we recognize that the force, that the component AB is a two-force member in equilibrium. So we know that the force at B must be directed along the line joining A and B. Yep. So let's see what I've done here. Okay, so I've just written that down for you. So when I fix up my error in my solution, you'll have a copy of this so you can remember that. All right, so that's what we just said. So there's our line joining AB. So we just got to do some trigonometry to find this angle. So it's just inverse tan 2 over 1.5, so opposite over adjacent. And for those of you who are on the ball with your 3, 4, 5 triangles, right, you'll recognise that again, this is a 3, 4, 5 triangle. So we've got here, this side is 3, or 1.5, but 3, and this side is 2 times 2, which is 4. So therefore, the length of this side will be 2.5. Yeah. So the 3, 4, 5 triangle. But if you don't recognise that, that's fine. You can just do it using the trigonometry. All right, so that's that, and then our force here at B will be along the line joining A and B. Now, if we put our force here, is it going to be acting up to the right or down to the left? Up to the right or down to the left? Okay, so one person thinks up. Up. Okay, how do we know? What do we use to work that out? Moment, yep. Moment about which point? Point C, yep. So if we take moments about point C, right, the only force acting on the body that's causing a moment about point C will be this weight here, W. Right? So we've got held at point C, it might be this way, held at point C out here, we've got the weight pushing down, okay? So tending to rotate this thing around clockwise. So in order for this to be in equilibrium, you've got to have a force pushing up to the right at B. Right? So the vertical component of the force at B must be acting in the upwards direction, in the upward sense. All right, so I just put on there, so I just put the line of action. So I can do that first because it's a 2-force member. And then now our horizontal component, that passes through point C, vertical component will be the one that's resisting the moment generated by the weight. Okay. If we took moments about point B, that would help us to work out the sense of RCY. So I think someone put in B as where you took moments about. If we take moments about point B, then yes, we can look at this. So is RCY in the correct sense? Yes or no? Okay, so we've got 1 no, we've got 2 no's. Awesome. I can see learning happening. All right. Yeah, and how do we know? Took moments about point B. So we've got point B here, weight is pushing down. So at the other end, we need to have RC pushing the other way, all right? And it's now 5:51, so I need to finish. Let me just I just did the moment calculation. Oh, too far. All right, who can see my error? All right, we're finished. We've gone over 10 to 6. So thanks for your contributions, everyone. Hopefully that was helpful to you. You can see my error. And how did I know it was an error? Minus 4.5?
No, that's positive. So I'm actually heading upwards.
Okay, so the negative sign is correct, right? Because we just went through that exercise to work out that RCY was in the wrong sense. Also, no worries, see you, Hichan. Yeah, so rush, leave if you need to. Just happy to stay and chat for those who want to chat and can find my error. And also how how I knew it was an error. So I actually went further than this, as you can see. I went further through here and I got to here and I thought, hang on a second, this is not right. There's something wrong. We'll go back here and see if you can see where my error is. All right, so when you're writing your solutions and you're thinking about getting marks for them, right? Often you think about it in terms of, well, someone's got the solution and they're comparing the solution with what I've done. When in reality, that never happens, right? No one's going to ask you a question that they already know the answer to. Right? So you have to be able to look at your solution and be able to think, oh, where have I gone wrong? RBX in the moment equation. Okay, so that's, I didn't forget RBX. Right? So look here, right? Where am I taking moments about? Right? So again, so important in your understanding of trying to work out what I've done here is to look at what I've written and say, we're taking moments, right? Good. Whereabouts am I taking moments about? Okay, it's impossible to check this equation that I've written here if I haven't written B here, right? If I hadn't written B, what might you have guessed I'd taken, or where might you have guessed I'd taken moments about? C, right? The usual thing is to take moments about C. Right? It's kind of a, you see the two unknown reactions here, oh, take moments about C, right? I looked at my problem and I thought, oh, hang on a second. I can actually take moments about B in this case and calculate for RCY as my one unknown because RCX passes through point B. Yeah, Nicholas got it. Not quite divided by 4. Oh, okay, you divide by, so it's 0.5 divided by 2. Yeah. Right. So you win the prize. I don't know what the prize is. So just going back to SETI, isn't it the same to choose any point as the moment? Yes, you can choose any point you like. I think this is the question you're asking. You may be asking something different, but I could choose. Let me grab my pen. I could choose this point down here. Call this point X. Right? I could take moments about that point down there if I knew the distances to that point and still solve the problem, right? This is just a stupid point to take moments about, right? Or I could take moments about this point here, point D. That might be a little bit more of a sensible, right? If I took moments about point D, a little bit more sensible. I know all my distances, but what would I end up with in my equation? Two unknowns. I'd have the vertical component of RB and I'd have RCY. Okay, so taking moments about point D won't help me very much. Right? Well, it'll help me a little bit, but not as much as taking moments about point C or point B. Right, and the reason, so just going back to this error here, so yeah, so Nicholas found it. If I took this over to the other side, it's W times 0.5 divided by 2. Right, so I just did 2 divided by 0.5, so I had it the wrong way around just in my haste. But when I was thinking about my solution, so is RCY W over 4, yes. Right. So when I was looking at my solution, I was thinking, well, hang on a second. If I've taken moments about point B and I've got W acting here, and W is 490 newtons, right? Then, and my reaction over here, so here I've got 2, here I've got 0.5, does RCY need to be bigger or smaller than W? It's got to be smaller, right? So just stopping and having a think about what the relative magnitudes of these things should be made me realise that I'd made this stupid mistake. All right, Norris, Sethi, see you later. See you on Thursday or Friday. Well, you'll see me, I don't see you. I wish I did, but anyway. So when you're doing so Nora still here, yeah, see you, Fadi. So yeah, when you write your answers, so if this was the final answer here, you should see in the calculations, in the working out, that there's a negative sign here. And then if you wanted to write final answers, RCY equals 1962 newtons down, that'd be fine.